Okay guys, so what we want to talk about in today's video are some of the formulas dealing with electric potential, okay? Now if you remember from Physics 1, we have some lessons about energy and forces and work. All of these things are still going to apply when we're talking about electric fields. All we need to do is find what are the new expressions relating to fields that we can apply to these ideas that you guys already have, right? So first of all, let's just review some of the formulas that we had before. So we have our electric field formula. What I've done here is just use a capital Q for the charge that is generating that field, right? And so I did this to make this a little bit simpler rather than using Q1 and Q2. So we have our formula here. Remember that my electric field is my K constant times whatever charge, let's say this is my charge, is creating a field, and then my distance from that charge is my R, right, my radius. Okay, and then when we wanted to calculate force, this was actually that same field, whatever was created by this charge, but now I've actually put in another charge out here. Maybe it's positive, maybe it's negative, and this is our test charge, okay? And then so now we have a force between these. Before there was no force present, just a field. Now there's an actual force, either repelling or attracting, depending on the charge that we use. And so we just have to multiply in that new Q with our previous expression of field, and this will give us our Coulomb's law, our force between two charges, right? Okay, so using all of these same pieces now, let's talk a little bit about potential. So if you remember, for potential energy, this was the capacity for something to do work, right? So all of my charges have some capacity to do work. For example, here I have some source charge. If I put out here a negative charge, okay, there is a force that is trying to bring these charges together. Let's say we fix this charge so it doesn't move, so only this small negative charge moves, okay? So this charge, being my source, can move my test charge a certain actual displacement, right? So it can move it, and when it does that, it's performing work, right? So remember, we're going to take in all of these examples that we've gone through before in Physics 1 and start applying them here. So the way that we define how much work can this do, this is my potential, right? So now we're just going to call this electric potential, and we're going to call this V. So everything when you hear terms like potential difference and voltage, and here we're going to call this electric potential, all of these things are kind of, they're describing the capacity for something to do work, right? So the way we're going to define this is whatever my field is, right, times my displacement. I think I'm missing something here. I must be missing my, okay, so what we have here is I have some electric field, and it can push some charge over some distance, right? So this is the potential of a field to do some work. And so here I have it in terms of electric field and some distance. But if it was this right here, then what I would have is, when I talk about my potential, this would be K times my source Q over my R squared. And then the most work that this could do, the complete potential that it ever has the capacity to do, would be how far exactly can some test charge move, right? So in this case, it would be the distance from my source charge to wherever it is, which is also R. In this case, D being my displacement is also R. It's not necessarily always going to be R when we talk about work, but this is the complete potential that we have to do something. It is also R, so in this case, my D here will be equal to R. these will cancel, and I'll have something like K, Q over R, right? So we're using all the same pieces here, just now giving us some new expressions that we have, right, for potential. Now, how much work does the charge actually do, right? So this is kind of the difference now between field, which we have potential just from a field, but now we're moving into like an analog of force. If we apply this force to an actual charge, how much work does the field do? You'll remember that we have this expression for work from mechanics, and what we use when we do this is I apply some force to an object, here can also be a charge, and I'll apply it over some displacement, right? So in this case here, I can apply my force, which is Q times E, and I can apply it over some displacement. Now here, I'm going to keep it as D because this displacement is not necessarily the entire distance. It could just be halfway, or it could be repelling, it could be the other way, but maybe only some distance, right? So I'm going to keep this here as D, just so you know. But there is another way for us to define work. You probably did this also in Physics 1, and this is work is my change in energy. Work is describing when I transfer energy to or from something, right? So when I perform work on an object, I give it energy if I perform positive work. I'm giving it energy. So in our case, we can either give it potential energy or exchange that potential energy for kinetic energy. In this case, we're changing some type of energy here when we do work. For example, when I have a test charge out here from this positive charge, it has a certain potential given by this expression right here. But what is its new potential if we move this to a point right here? Okay, now it has some smaller potential, okay, but it has been moved. Its total potential energy has been changed, right? So we have this change in my energy. So all I need to do in this case would be, I would put this maybe as whatever my final potential was minus my initial potential, okay? So in this case, what I can do is, we're missing one piece here, missing one little piece here, and that is, what am I actually moving, right? So I'm moving this through some potential, but what am I actually moving? It's my charge, right? So we have another expression here that we can use to find what was my initial potential, right? I had some charge at some potential, and then now I have my charge at some other potential, and I just need to find the difference between these two states, between this initial state and this state. How much has it changed? Well, that's how much my work my electric field has done, right? So here, the initial, we can call this work as well. So we have now a pretty good system of formulas we can use to find different aspects such as my change in energy, electric potential, force, electric field, okay? And then we can also keep using these tricks from Physics 1, where, for example, if I had a ball above the ground, its potential energy, let's say it was equal to 1 joule, okay? When this thing falls down to the ground, okay, and hits, it exchanges all of that potential energy for kinetic energy, right? Here my kinetic energy will also be 1 joule, okay? Because gravity performs some work on the object and we have conservation of energy, right? So this is going to be the same sort of case where we can actually take a charge and accelerate it with the electric field and use this same idea of how much work did the electric field apply to the charge, and then that will tell us how much it was accelerated by that charge, right? So we could do this also as in work is my change in kinetic energy. So it'd be 1/2 mv final squared minus 1/2 mv initial squared. And these just now being the mass of my charge and the speed of my charge. We can still do this with our ideas from before using, now considering electric potential, okay, as another method of finding work.